Thank you, Chairman, and ladies and gentlemen, good morning. And my topic is micropit formation on the rolling contact fatigue of bearings through crystal plasticity model coupled with cohesive finite elements. My name
sorry.
is.
Could we check the microphone, please? I think it is not working. Okay.
It's not for.
We will check it. You can just submit.
Right. My name is Shuxing Li from Ningbo University, China, and here's the contents. And bearings are on rolling contact fatigue, and they normally fail through micropit formation and development. Actually, pits are formed at a very early stage of a rolling contact fatigue. I call it RCF in short. And especially for bearings under conditions of dynamic loading and non-ideal lubrications, such as wind turbine gearbox bearings and heavy load bearings. We look at the surface of bearings. Here's the pit. It's optical morphology. Then we section the bearings. We see a lot of cracks. Those cracks are actually two formations, either from surface or subsurface. But here I'm only talk about surface initiated cracks. And there are many cracks. If you look at this, they go along like within 40 degrees, and then at some point they shift. Rather than going into deep, they shift to parallel, and those cracks link, and then form the pits. And what I'm talking about here is the micropits ranges from tens and hundreds of microns. And mostly researchers are focused on crack initiation, but different from conventional fatigue. In rolling contact fatigue, actually, the crack initiation takes up only 20%, less than 20% of total fatigue life, but it's mainly the crack propagation that leads to the failure. So, what we are concentrating on is crack growth. But for those work which deal with the crack growth, they found the crack normally grow along the boundaries, but actually when we section the bearings, we found crack growth within the grains transgranularly rather than along boundaries. So there are some inconsistent results between the modeling and the experiment. That's what I'm concentrating on. So the questions are, how does those micropits form? And since the stress varies with the depth, how does the crack propagate and transgranularly and intergranular? That's my question. With those questions, we did RCF tests, and I'm not going into detail. And we found quite a lot of cracks going parallel along the surface. If you look at this one, they're going very shallow and parallel, which means it's not related to grid boundaries. It's actually shear stress dominated, and the EBSD results showed that those cracks actually go inside the grids rather than along boundaries. So here's the features. And in rolling contact fatigue based on Hertz contact, the stress distribution is here. The maximum shear stress and mesize stress is at the subsurface. So how does those crack initiate? Because at the contact edge, both here is known, because the rollers going along the surface at the contact edge, that's a very high stress concentrations here. This is how the crack initiates. And then those cracks that goes parallel and they shift towards surface or either stop growing, and those cracks link with each other, they form the pit. Here's the cracks forms. And because the model based on Hertz contact is unable to explain crack growth on macro level, so how could those stop growing, or why they shift towards the surface rather going into the deep? So that's question. we model the crack propagation based on crystal plasticity coupled with the cohesive elements. As for CP, it's mainly to consider the microstructure effect, but for crack growth, it has to be the cohesive element. And here's those fundamental equations. I'm not going into the detail. Here's the RVE models. What I want to stress here is that we put 1.8 gigapascal contact stress on the surface, and then a tangential traction force along the surface with the coefficient of friction 0.1. Here's the details, and of course, here is the calibration and validation of the model based on tensile tests. And I'm not going into detail. If you're interested, you can go for these two publications. And to further validate the model, we compared the model with the results from the Hertz typical contact, and those results agrees very well, and which means that the model is valid. Here's the results. And because damage and equivalent plastic string accumulates with increasing number of cycles, we initially preset parallel cracks based on our experimental observations, and those cracks, the size of grains and crack length is exactly the correlates with the experiment. And so we found as number of cycles goes, and cracks that grow or the link and then form the pit. Here's the result. And here is one. And also we found those cracks that grow transgranularly, even if we put initially we put cracks along the grid boundary, and like these A and B, we want to know how those cracks initially at the grid boundary that propagate. And the result is quite interesting, and I found actually the damage within a crystal is much greater than that at the grid boundaries, which means those cracks will grow because the damage accumulates quickly than at the grid boundaries. And these results is consistent with the EBSD here. We found those cracks grow transgranularly rather than along grid boundaries. And because the RCF is dominated by shear stress, those crack growth actually dominated by the shear stress rather than volume stress. And at some point, as I said, not those cracks which initiated at grid boundaries, actually they shift to transgranularly, but at some point that shift to grid boundaries also. So how does this happen with this? Because those are EBSD results from experiment. We found those cracks that go almost 93% of cracks we estimated from statistics show that go transgranularly, but as they go certain depth, they shift at this point, like transition point, they shift to intergranularly. So how does this happen? So we did this simulation as well, and here's the results. And we compared without changing anything but the green orientations. For this one, we did the first simulation, and the second we remain just change the B and A and C. The green crystal orientations will change, but remain everything same. And we found different results. For example, if you compare these two A and big C crack, the crack growth path completely changed, which is all because the crack growth path is significantly influenced by orientations. The damage accumulation and stress are quite much larger or after change. And cracks are more prone to propagate at gray or at grains with the preferential crystal orientations. Here we compared the damage and shear stress before and after changing the crystal orientations. And here's the illustration of a crack growth and the micropit formation process. It involves 3 stages. First, it's the multiple cracks initiate due to stress concentration, and then transgranularly and intergranular propagation. It depends on crack depth and shear stress, but strongly influenced by crystal orientations. Then crack coalescence leads to micropit formation. Here's the conclusion. I'm not going into detail, but during the modulation still we are quite confused since the near surface cracks are significantly refined, because in RCF, because there's quite large plastic deformation near the surface, grains were greatly refined. So, but in this model, we didn't consider the gradient in the grain size. And also, so the one question is that since crack near the surface grow transgranularly, is it necessary for bearing materials to refine the microstructure? Even if you refine its grow inside the grains, so that's the question we are not still resolved. Okay, thank you very much.